So, um, so what we were talking about last time was how to extend these ideas to multiples. So, sorry, let me share my screen. So, how to extend the ideas to multi-class classification, and so we ended up, if you recall, by sort of introducing this softmax function. And what it does is that takes a vector, real value entries, and raises each component to an exponent and then divide by the sum. So this is guaranteed to create a probability vector. So a vector that has non-negative entries. It's actually strictly positive entries that sum to 1. So the use of this is that it allows us to enforce the probability constraint without worrying about like these constraints really. So in the input domain here, the vector can vary as it likes. So it can like be negative, positive. I can add two things up. I can't add, for example, two probability vectors up and still be a probability vector. I can't subtract necessarily. So if you want to do gradient descent on the space of probabilities, you have to be careful to stay within the space of probabilities. So you can take a gradient step and project back to probabilities, but this is going to be helpful because if we work in this space, sometimes these are called logits. They're generalized versions of logits. So we work with logits, which are the input to the softmax. Then we can work on constraints. And so the idea was that the input to the softmax. So we write the probability of y given s of x as some, like s applied to some function of x, which we parameterize by the parameter, and then we chose the form of this to be a linear function of x. So that's the natural generalization of logistic regression. Because in logistic regression, if you remember, what we had was that the probability that so the logistic regression side note. Logistic regression. So probability of y equal 1 given x is equal to x. This is equal to sigma theta transpose x. This is a general linear function of x that maps. So if I want to map a vector in Rd to a vector in R, and if I want a linear function, this is the most general form, right? So a 1 by d vector multiplied, like matrix multiplied by x, basically. So we argue that in general, if I want to generalize to the multi-class setting, I want a linear function that maps Rd to Rc, R to the C. So that would be the matrix here gets multiplied by x, and it produces a vector in Rc. So this would be C by D. Okay, so if I have a C by D matrix multiplied by x, that's how I can generalize. I can generate a general linear function of x. So that's the natural extension of this idea. So we replace the sigma with this softmax, and replace this linear functional or function with this linear function. So the only thing that changes here is the dimension of the output of this linear function. Now it's c-dimensional rather than one-dimensional. Really here we needed to do like two-dimensional because c is 2, but there's a homework problem that you figure out. In this case, we just need to model just one of these probabilities because the other one is 1 minus this. Here we have like C classes, you need to model at least C minus one of them, but here we are modeling all. So there's this tiny difference here. So this model is not exactly this, but it reduces to this. But because we're modeling all the probabilities, there is some redundancy in theta. So theta not all thetas produce different models. So there are some thetas that produce the same model. And you see in your Hort problem, for example, that if you add a constant to every one of the coordinates of the input of softmax, it doesn't change the value. Okay, so I can shift the vector by a constant amount. So that means for the softmax problem, for the softmax regression, let's go to the, so it means that if I subtract a vector from every row of theta, that's not going to change the model. And that introduces some redundancy in theta, which may or may not be useful. Okay, so that's the softmax problem, right? So softmax regression. So the way we write it is, so you apply this S to this theta X, and then you pick the y coordinate. So this is a c-dimensional vector, c by y, and the y coordinate gives you the probability that you observe class y, right? So a little bit of like neural net sort of picture is, so this is, we can view it as like D features go in. So there's this mapping that maps it to, like, let's say C, let's say we have 3 classes, C classes here, and each one is a linear function of D. So this is like theta. These are the pictures that people plot usually. So theta, what this is saying is that this is theta X. So this is X. Theta X sort of basically every coordinate is a linear function of all the coordinates of the input, right? So if you imagine this is like the first coordinate of this is just going to be a linear function of all the coordinates here, and the weights are going to be the rows. So for example, here we have let me do this with 2. Yeah, this is bad. So this is here. Imagine this was 4, x4, and then I had theta 3, 1, theta 3, 3, 3. So the first coordinate would be this times that. Okay, so these are those weights: theta 1, 1, theta 1, 2, theta 1, 3, and theta 1, 4. We need another column here, right? And so on. But the picture doesn't like matter, but you'd see these, you're already like seeing some sort of like a neural network if you want. And then you apply the softmax here at the end. So this is like the softmax. And then it outputs, again, this is X. I should say this is X. This is theta X. And the output of this is S theta X. This is also has 3 outputs, and these are the probabilities of the 3 classes. So if I want the white class, I would pick the white element. So that's my notation. The probability of y is equal to y is the white element of this vector. Okay, so that's like the picture if you want. So this is a linear, like again, terminology of neural network. This is a linear layer. And then there's the softmax here. And the output gives you the classes. So this is called a hidden layer. Right? You're already doing neural networks. You're not doing much system like softmax regression, but if you want, you can say you're doing neural networks. Okay. It's just the softmax translates things. So it's worth understanding that this translates things to allow us to not worry about the input could vary anywhere. So now the input can be like a linear function of the input to the softmax can be a linear function of the actual features. Okay, very nice little compact formulation of softmax regression. It's a generalization of the logistic regression. Okay. questions? Or what do we do next? So we'll introduce the model. What should we do next? What do you do like usually in machine learning? So you have a new model, shiny new model. Sorry?
Evaluate it.
Evaluate it, but you have to first train it, right? You have to take it for a test drive, see how it, like, you're evaluating it comes at the end. If you have to like fit it, or like the statistician would say fit it, machine learning people would say train it, yes.
So you basically, for this model, you would have to train it to find the theta matrix.
Yes, there's only one parameter here, theta. Implicitly, I'm assuming that again, x has like the augmented with parameter, like sorry, in a feature of 1. So sometimes you write it as, instead of writing theta x, so explicit intercept, I might write x as like 1 and x tilde. This is like the actual features, this is augmented. So theta x would be, let's say w x tilde plus b. So if you imagine this has like a part which is b and a part which is w, right? And then this is 1 x tilde. So you get, this is b, this is w. And so sometimes you'd see that this has 2 parameters. So if you do like PyTorch, there's a b and there's a weight matrix. So that's called bias weight, right? But for compactness, we have just a single theta. Yeah, but that's the learnable parameter, again, terminology of machine learning, learnable parameter. This has one parameter to be learned, just statisticians would call it just a parameter. And you have to find this theta. So you have to fit this. So there are 2 things. So one is whether your real data is generated from some model like this. So this imposes some assumptions on how these probabilities behave. So if you think about the original setting that we discussed, we have a joint distribution in x and y. This is assuming a very particular form for the conditional distribution of y given x. So this, you can imagine that in the ideal situation, there is a theta star here that's actually there and generates the y's given x. And then when we fit it, we just imagine a general theta, and then if we fit it to the training data, you get an estimate of that theta star. In practice, there might not be like a theta star. The model might be, this is just an approximation of the true distribution. The true distribution need not follow this model. But the simulation that I'm going to show you today, you're going to actually generate from this model. So there is going to be a true theta star, and then you can verify that. Now, if I have data, if I go and train it on that data, can I recover the theta star? Or what is actually more important is, can I recover these probabilities correctly? Because as I mentioned, theta star is not fully identifiable, because I might end up with a shift of the rows. That would give me the same model. This you can verify for yourself, that if you add a constant vector to each row, because of the fact that the softmax is invariant to a shift, that wouldn't change the output of this. No matter what, like as a function of x, it's going to be the same function. So you get the same probability model. The statistician would say that this parameter theta is not identifiable, because 2 different thetas could give me the same probability model for y given x. But you're going to get it up to a shift, hopefully. As you will see, it's not that easy. But like machine learning people don't care about estimating the parameter, they care about the prediction. So you want this to be good, not the parameter. The parameter might not be good, but you want the prediction to be good. The output of the model, the probability model, you want it to be good. the criteria for us is not parameter estimation. The statisticians worry about parameter estimation, whether this is a good model, whether we are getting the parameters, like uncertainties for the parameters, these all go like out of the window in machine learning because you don't care about the parameters, not of interest. It's just an approximation to the true model. You just care about the prediction. Sort of. Like at least by majority of the people, not everyone in machine learning. That's not generalized, but the prediction is the main like goal. Okay, sounds good. So how do we do that? How do we actually train the model? I have a new model. How do you propose we estimate theta? Like, do we have to estimate theta? There's just one theta that I have to estimate. What do we do for logistic regression? How do we estimate that parameter theta in logistic regression? Just remember this. Anyone remembers what we did? There was this general procedure. How do you estimate the parameter in logistic regression? And I give you a training data like xi, yi pairs, I from 1 to n. There's a general procedure like for fitting a parametric model.
You minimize the loss.
We minimize the loss. It's a form of empirical risk minimization, but how did I get that loss? How can I find what loss would be useful here? Like matching the current model that we have.
Change the threshold.
Sorry?
Change the threshold.
What threshold? So thresholds here, yeah, come later. Let's say, once I fit this model, I get a theta hat here. Then I can, for any given x, I get a vector of probabilities. Then I can decide which decision I would, like hard decision if I want to pick a class. It's like a little bit more fancier than thresholding, but we'll get to that. Yeah.
So if you're predicting the probability using the softmax function,
yeah,
then you will be deciding the class based on like the argmax, right? You would maximize the
good. Yeah. So yeah. Okay. So that's yeah.
And then so to find the loss, you could basically do like if you have, I guess, n training 1 over n times the sum via the indicator.
Yeah, so we have training the softmax regression model. We have x1, y1, xn, yn. So let's see. So 1 over n. So this is the training data. So you form this indicator of, so can you say that again?
Indicator of yi.
Yeah.
Not equal to prediction from the sun. I guess
Argmax.
argmax.
Okay, level y. The model would be like S theta xi, right, over the y coordinate. Right, so that would be the decision rule. Basically, this is going to be my delta. Let's call this delta star of theta if you want, divided xi. So if you have this softmax model, if this is the true model, then you can argue, if you remember, what is the Bayes rule? The optimal Bayes rule here. What does the optimal Bayes rule does? Like, if you go very like to the beginning, you would, for the 0-1 loss, if I have the 0-1 loss, what is the optimal rule? Arg mean of the posterior loss, which would be like if it's 0-1 loss, it would reduce. You go back to some of the things that we did, we used to take the argmax of this over y. So the Bayes rule here for the 0-1 loss would take the argmax over y. You take the argmax of this, which is the natural thing to do. So that's the Bayes rule in this problem. So if you're minimizing the 0-1 loss for any given pair of x, like for any feature x, you have to predict the label that maximizes this probability. This probability happens to be modeled like that, so we maximize. That's basically really the Bayes rule in this model for that particular parameter. So this is good. So this is going to be an interesting loss. There is only one. So this is our like prediction. So this is like basically y hat I, if you want. Okay, and it's a function of theta. So I can take this as my loss and try to minimize, vary theta c when this is minimized. There's only one problem with this. Little problem. What is the problem with this? Yes. Yeah, so this is not a smooth loss function. So it's not easy to optimize. In particular, the gradient is basically going to be sort of zero most of the time. So it's like 0-1 loss, the gradient, it's not differentiable. Where it's differentiable, the gradient would be, let's not say zero, but it's not easy to calculate or like not differentiable at all. So it's not like useful. It's useful for evaluating the model. So you can evaluate the model. That's exactly what we're going to do. So this is going to be this is the training 0-1 loss for this model. So if I have a theta, I can use this to evaluate the model. So training, like empirical, like training error, or for the 0-1 loss, or training risk, if you want. So minimize over theta, hard to do, since the loss is not smooth. So what should we do? Yes. Yes.
Why I have it? I'm sorry, I can't really read your handwriting compared to that. Can you just clarify why I have this?
Yeah. Okay. So this is this on imperating is y hat I, right? So what I wrote is like y hat I is I'm writing it. This is just notation. This is the rule, the optimal rule applied to xi, which is argmax over y of this. Right, but that's really our prediction. Okay, right. This is just notation. It's just given any x. So this is saying given any x, that's how I should predict a class, like a hard class, if the softmax regression model is the true model. If the model is correct, this is our rule, optimal rule. Yeah. So that gives you a hard class. So this is going to be in 0 to c. If you remember, I'm using vectors are indexed by 0. So it's also the notation to use. So it gives you one of these classes because this is a vector c-dimensional. The first coordinate is indexed as 0. So argmax gives you the index of the coordinate that is the maximum. So that gives you the class. Okay. Any other question? So how do we deal with this? How do we deal with this in the logistic regression? So you had a differentiable loss, multiple versions of a differentiable loss. How do we get the differentiable loss? Quadratic loss. Quadratic loss. So if you do yi minus y hat I, this still has the same issue because argmax is not differentiable. It's a little bit better than that, but not perfect. And then this doesn't really make much sense because these are labels, right? So the way I wrote it, it's a label. There is a way to fix this. So can we use quadratic loss, actually? Is there a way to use quadratic loss? If you think of it at the level of probability, so these are probabilities. So the softmax is basically, it's actually a good exercise. I did not anticipate this, but this is going to be basically like, so let me write, how should I write this? Yeah, so I'm going to write it as the transpose of it. So it's going to be a vector, C-dimensional. The elements give you the probabilities of belonging to each one of the classes. So let's say there are 4 classes. You'd get something like that. So this could be like 0.1, 0.3, 0.01, and then so that it sums to 1. Okay. Yi is like a label, but I can encode it to match this dimension, like C. How can I encode y like that? Yeah.
You can put if it belongs to like class 1 or 2, you could put that as 1 and everything else is 0.
Great. So I for example, if yi is equal to 2 here, this is class 0, class 1, class 2, class 3. I'm going to put the 1 here, 0s everywhere else. So if the class is like 0, there's going to be a 1 here and 0 everywhere else, right? So this is an encoding of the label as a binary vector of length C. This is called one-hot encoding. Okay, it's a particular kind of encoding. So this mapping is called one-hot encoding from probably electrical engineering, because there's one hot wire, the rest are 0. One coordinate is 1, which depends on the class. Now I can compare this to this, because if, for example, one of them is very large, it's like when predict a class of, for example, maybe this is class 2. If I'm doing correct, maybe this is like 0.9. The rest are very small, 0.05, 0.05 here, and 0 here. Okay, so there's going to be, this is going to be very large. The rest is going to be 0. So it makes sense to compare this directly to that. And so if I form like a vector, every row here is going to be, I'm going to write this as y tilde I, let's say, transpose. So it's going to be y1 tilde transpose up to yn tilde transpose. This is going to be y tilde. And then I'm going to put these into, again, this is going to be transpose, and then s theta x n transpose, right? So this would be n by c, right? Then I can directly compare these two matrices. Okay, so row by row, and I can form this divided by this, and then the L2 norm, Frobenius norm, actually. Okay, so let me do it simply. So I'm going to do like y tilde I minus s theta xi. This is going to be a vector, c-dimensional L2 norm, and then summation I from 1 to n. and then 1 over n. Okay, that's like each row compared to the corresponding row and then L2 norm. So this just compares this vector to that, takes the difference, and then form the L2 norm. So this is reasonable because when that softmax is like peaking at one coordinate, which matches the true label, the difference is going to be small. So the ideal case is that if this is 1 here, 0 elsewhere, then the loss would be 0. So that's a reasonable thing to do. You can form this quadratic loss. So this is good. And I can also write it as a matrix sort of. If I want to do matrix, I'm going to write the difference of these two matrices and the Frobenius norm squared. Frobenius norm squared is going to be basically taking the difference of every coordinate. Yeah, let me mention that maybe after I mention the matrix format. So is this sort of clear first? So that's a value of loss, and this is going to be differentiable. Because softmax is differentiable, the L2 loss is differentiable, so the whole thing is differentiable. I can actually minimize this. Okay, this is good, and it's a reasonable loss. Questions? So the matrix format, the nice thing is, let me mention this. So I'm going to use this idea that, so you have this map that maps x to s theta x, right? This maps from RD to RC, but I'm going to apply this to each of these x1 up to xn. I'm going to use like the PyTorch sort of notation or mechanic. So if I have my data x written as n by d, so each row is going to be one of these x1 transpose, x2 transpose, dot, 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 xn transpose. This is also how you like represent data in linear regression design matrix. Okay, so this is sometimes called the batch dimension because that's sort of our, so batch and sample sort of almost synonymous, like machining. So this is the batch, and then this is the input dimension. Then I pass it through this model that I have, and what I'm gonna yeah. So in code it's easier to write, but x passes through. So this is called as f. Where should I write it? Mathematically, it's a little bit harder to write. But I just want to define. Let's define sort of softmax regression. So, okay, so let's call this the model. So what I'm going to do is apply the model to x. So what it does is that it's going to apply it to basically each row. Okay, so it keeps the batch dimension, applies it to each row, and it would just give me model applied to x1 transpose up to the model applied to xn. It's like there's a parameter theta here. Right, so this is going to give me an n by C matrix because each one passes through this, right? So you pass through row by row, you keep this dimension, but you get a C-dimensional vector here, right? So x1 is B-dimensional, passes through the model, gets mapped to a C-dimensional, and then transpose, you put it there. So this is going to be an n by C matrix. So that's how usually like you implement these, and PyTorch sort of functions that are implemented, they act like that when you apply it to like a matrix that's n by d, it's going to apply it to everything, like if it's a matrix or a tensor, to everything that's not the first, to every element of the first dimension, like in parallel, like this, and then put back together everything. So you're going to get your model applied to every sample, and you just flip the dimension of the input to the output. Okay, so in this notation, this would be my y tilde minus model x. And then when I subtract the two, I'm subtracting the matrices. You can verify that this is going to be the Frobenius norm if I want to write it. The Frobenius norm basically is just this, or it's just the L2, the difference, coordinate-wise difference of the two, and then squared and the sum across everything. Okay, sort of fine. So that's then this depends on theta, right? And so I'm now optimizing over theta. If you want, you can mathematically write it in terms of the softmax. So if you have a linear, okay, so maybe mention, so is this, like, I'm going to mention later. So is this okay? This is good. So that's reasonable. You can form this loss, or if it bothers you, it's just do the top one. Y tilde minus model xi. That's also true. And minimize over theta. So that would work. Differentiable loss, and then we can optimize, find the theta. Sounds good? If I wanted to do mathematically, yeah, maybe do it later. Okay, maybe do it here. So just a side note. So if you have a linear model or a linear layer, this takes x, maps it to theta x, right? So if I do this batch operation, if I have x, which is n by d, I want to pass it through this linear model row by row, I get n by c. This is c by d. So how do I write mathematically the output? I want to mathematically write it in terms of matrix multiplication. So in PyTorch, this is just a layer. You pass your x through it, and it does it for you. So automatically just goes apply the linear model to each row, you get n by c automatically. But mathematically, if I want to represent it with matrix multiplication, how should I write it? So this is like x1 transpose, right? When I pass it through, it would be theta x1 transpose, right? Up to theta xn transpose. And so what happens if I transpose a product of two matrices? Yes, yeah, so you flip this. And is there a simplification that carries through? So you can write this as this. If you verify, this is n by d, this is d by c. If you multiply, each row gets multiplied by this entire thing. So that's how the matrix multiplication works. So this is x times theta. So if you look at like PyTorch documentation, this, so we'll see this is a class in PyTorch, like NN linear, like maps, let's say D to C. So what it does is that if you give it X, it goes in, it has a parameter, it produces X theta transpose. That's how you apply a linear model to your data mathematically. Okay, so you multiply by the theta transpose on this side, and the other side, it's as if you like multiply each row We'll pass each row through there. Okay. Sounds good. So you want to do like batch, sort of in the language of machine learning, batch application of a linear function or a linear layer. So you multiply on this side, assuming that the rows of X have your data, and it does this linear transformation. Okay. Sounds good. Okay. Just a comment. Okay, so this is good. So this relies on doing one-hot encoding, right? You do one-hot encoding and compare these. We can call them soft probabilities or soft assignments to classes, or just the probability of classes. But there's another way. This is actually good. This would work out. Maybe I can assign it as homework problem. This would be a very good homework problem. This is one way to train the model, right? There's another way. This is not how we did logistic regression. How do we do like fit logistic regression? So approach 1. Quadratic loss. What is approach 2? What is the general approach to fit the parametric statistical model? Yes, there's going to be another loss with log involved, but like, is there a general principle that I can follow to arrive at that loss? What's a general approach you know to do estimation in parametric models? Great, MLE. So that's what we did. This is what we can do here. So we can write down the maximum likelihood estimator. That would give me a general procedure. Once I have a probabilistic model, I can write down the MLE. So how do I write down the MLE? So what is the likelihood here? Remember that Ln. So approach 2. The MLE. So likelihood, what was the likelihood? Yeah.
It was probably from swimming y I to mean y1 to yn given this given the value of family.
Yeah, so I forgot that I used this notation for the likelihood or the log likelihood. I guess I used it probably for the likelihood. So this is the probability of observing y is given the conditional probability for us because we're specifying everything conditional on excess. So that's our likelihood as a function of theta. When you view it as a function of theta. And this turns out to be like product, if you remember, because these are independent draws. In this case, turns out to be like that. And then we, instead of maximizing it, we minimize negative log likelihood, right? If you remember. So this turns out to be a minimize. So this is a general procedure. To minimize 1 over n summation I from 1 to n negative log e theta yi given xi. So this holds in general for IID sampling. What changes here from the logistic part is this negative log likelihood of a single sample. Okay. So how do I write this in our case? So what is p theta yi given xi? E theta yi given xi. This is like a label in this, and this is in RD. We're assuming that we're coming from like a softmax regression. it's simpler than what you think. So if you have softmax regression, what is the probability of observing class yi given xi? Softmax. We wrote it multiple times today. Okay. Theta xi, and then the white-eyed element. So this is, remember, this is the probability, the model. So I'm doing yi here, xi. So you plug in xi, yi here, right? So because you're observing, yi for xi, so that's your likelihood. So you're going to go pick that white-eyed coordinate of that softmax. That's your likelihood for this particular sample. Does that sound good? You just plug in into this idea, P of y equal y given x is equal to x is s theta xy. Right? You're plugging in xi and then no y is yi. That's my observation. That gives you the probability. This is the probability of observing that particular combination of xi and yi under your model. So that's sort of from softmax regression model. This is where our model comes in. And so if I write this down, I get a nice logarithmic loss, minimize over theta 1 over n summation I from 1 to n, negative log s theta xi, and then y I can do a log here. Right, that's going to be my loss function. It's not quadratic loss, but it's the valid loss that comes from the likelihood. Okay. If I define a loss, which people call cross entropy, unfortunately, y and z to be negative log s z y, right? Where y is in the C star, z is in RD. So this z is a logit, multivariate logit vector, and y is a label. So this is called cross entropy, general cross entropy loss, unfortunately. It's better if they called it log loss, but I guess in PyTorch, if I'm not wrong, they call it the cross entropy and across machine learning. It's the cross entropy. It's a loss between a multivariate logit and a label, like multi-class label. But if you go back, it's very much like the log loss in logistic regression. Cross entropy would be between y and the probability. So if I it would have been nicer if this was y and then the probability vector here. So here softmax is absorbed into the loss, so it's between a logit, and so it would have been nice to have, I think they call it negative log likelihood, something like that in PyTorch. So you could have like negative log p of y. So p is a vector. This is in C star, and p is like in like a probability vector in 0 to 1 to the d. This would have been better to be called, like a better choice to be called. And then this would be like LCE of y and z would be negative log likelihood of y and SZ. This is very much similar to the relation between the binary cross entropy and the log loss. Why are there? So we could have called this cross entropy loss is the log loss, and everything is better. Life would be more consistent. But now people call this cross entropy. This is something else, if I'm not wrong. But this is most likely what people use as cross entropy. In any case, whatever you call it, let's call this what is usually called the cross entropy. So this is going to be a minimum over theta, 1 over n summation I from 1 to n, LCE, and then yi and theta times xi. So it has the nice flavor of having a linear map, and then some general laws. So again, very much like regression, it's like it's not like the kind of regression that you saw. It's like multiple response regression, but because this is a vector, this is also a vector, but it has a nice flavor of like measuring like how this yi, how close this is to that. Or if you want, in terms of this negative log likelihood, it would be like yi and then s theta xi. We'll implement it in this way. So this is basically if you think of it as part of the model, whether S is part of the model or whether S is absorbed into the loss. So you can absorb the softmax into the loss, or you can put it into the model and have a simpler loss. It doesn't matter. So people would do it both ways. The way we did it is softmax is part of the loss, so this is a little bit more natural. So this would be your prediction. This would be your y hat I. And multivariates, both of them are in RC, like not RC. Sorry, this would be this basically would be p hat, not y hat. This has the meaning of a probability. So p hat I. This would be more like a logit. But in any case, so once you understand what you're doing, it doesn't matter what you call these things. Okay, but this problem is often how people like train or fit softmax regression rather than quadratic loss. It just tries the loss from the MLE problem. Okay, sounds good. This is also a differentiable loss. Softmax is differentiable. You can see it's like a bunch of exponentials divided by the sum of exponentials. And the reason why it's called softmax, because it's actually the limit. There's a problem. In the limit, when you multiply, so it's like a smooth version of argmax. So this converges to argmax of u. Let's not do it, but if I multiply the input by beta and let beta go to infinity, we take the argmax of the elements of u. So this is like a soft version of argmax, not the soft version of max. It would be better to call it soft argmax. But again, as like it's easier to call soft max, it's called softmax. It's like a soft argmax. So it's differentiable and the loss is differentiable, so everything is good. Questions? So this is like a empirical risk minimization, right? With a different loss, ERM. If you treat it like this, the model is like a linear model or a linear layer. If you treat it like this, the model is a linear layer followed by a softmax. The loss is simpler, or it's just a linear model, linear layer with the loss being cross entropy, whatever you want to do. Both of them are ERMs for ERM formulation. For fitting the softmax regression. Sounds good. Everything is good. Questions? Okay, so let's do some demonstration. Okay, so what I'm going to do is like try to implement or like walk you through this. So this is on GitHub, so you can go work with it. But I want to also introduce you to sort of the way people like write down this model. And then once you understand this, like it's just a few steps to like build more complicated models. So this is like typical torch, and then torch NN is the to import from torch and like import torch NN as NN. So this is what we're going to use to get us these linear layers or some other stuff. And then from torch NN import functional as F, or like, so this is going to contain these softmax or other interesting functionals. So this is, we get used to this. So the first thing to do is like to look at what softmax does. So here I'm doing a 10, like, let's see. I'm defining a torch tensor, right? Get rid of this. So there's a torch tensor, and then I add 0 to it, and let me clear out. So if I run this, okay, we're gonna have a problem. So the size is 1 by 3, so you see double brackets here. So this is really a matrix. So it has one row, and that row is this vector. So 1 by 3, and then I'm doing softmax on dimension 1. So dimension 0 is the rows, and 1 row and 3 columns. So it's doing softmax across columns, across dimension 1. So if I do across dimension 0, what do I get? Softmax across, like, anyone has a guess? Softmax across, technique of probabilities, you just have one option. What will be the probability of that single option? If you flip a coin, there's only one possibility. What is the probability of that possibility? 1. So if I do this, I get all ones. So that's softmax on a single element would be just basically e to that divided by the sum of the elements, which is e to that. So it would be 1. So that's fine. If I do it on the first dimension, it's just gonna go raise each one of these elements to that power, and then divide by the sum of those values. So if I, for example, do 10 here, what would happen? So e to the 1, e to the 10, e to the 0, and then divide by the sum. So which element would be bigger? Yeah, so the bigger, like the middle one would, like you see, it's like going to be, this is like 0.99, the rest are like very small. So if I like do negative 10 here, this is going to go very down, like close to 0. The other two are going to be large. Okay, so depending how like the relative sizes of these are, you get different sort of, this encodes sort of the probabilities you see. The bigger one, basically, it's like roughly taking the argmax. So if this is 10, if I take the argmax, it would be like the second element, and you can see the second element sort of like close to 1, right? So it's like 1 hot encoding of the argmax function, right? So if I had the argmax, it would be 0, 1, 0. One hot encoding of the argmax would be 1, 0, 1, 0, and this is very close to 1. Okay, so this gives you the 1 hot encoding, like approximately the 1 hot encoding of the softmax. If it's like this, then the first two are like have equal probability. Right? The second one is smaller. Sort of clear, roughly what the softmax is doing. What happens if I add something to every element of the vector? Things are not going to change. So that's what I claim. And you can show it's just the relative sizes matter, not a constant shift. So this adds a shift. So you can see X is now 5, 5, 4. It used to be 1, 1, 0. It doesn't matter. Right? I can do this. I can multiply by, like add by 100. So sometimes it's good to like subtract. So if you, this is like a if it's like 1,000, this is safe. But if you do it in R, e to the 1,000 is going to overflow. So it doesn't make much sense. But like if I have like 1,000 here and like 900, numerically, it doesn't make sense to try to exponentiate. So you like subtract, for example, 1,000 from them. It's better. So subtract always like the maximum or like the mean, such that this is quite stable, right? This is not going to overflow. But I encourage you to try to do it in R and see what happens. So if I want to do this, I would do 1, 0, and -1, for example. It's similar to 1,000, 1,001, 1,00999. So just some ideas. Okay, this is going to. Okay, this is softmax and its invariance. Not very important. Questions? Just to get a feel of what the softmax is. So now this is how you define a linear map. So nm.linear, this gives you a map. So this is the input dimension. This is an output dimension, maps R2 to R3. So the input goes first, the output goes second. If you do this, it tells you that it's a linear map. This is like our theta, but it's just a function, right? So what happens is that I can apply this. It's really an object. It has a bunch of stuff in it, including the weights, but I can apply it to data. So if I look at this, it says there is a bias. Bias is true. And if I look at it has a property, weight, and that property has a property data, and it has a property bias, and that has a data. So these are the weights, and these are the biases. So the weights are 3 by 2, right? Because it maps from R2 to R3, right? So remember this. The input dimension is 2, so there are 2 rows, 3 columns. So this gets multiplied by 2-dimensional vector produces a 3-dimensional vector. Okay, so that's like our theta. Our theta is really this one concatenated as the first column of the weight matrix. That's what it is. So the way that it is initialized is random. So if I rerun it, it creates another layer. Not layer, but another object, which is a linear map. And if I do this, you can see the weights are changed. Because every time you create this, this creates that linear object or linear layer, and the weights are random. If you don't put this data, these are also objects, but these are now parameters of type. You can see the type is parameter. So there are like formally torch parameters. They have other features, so you can track them, register them, etc. But they have the data. The data is like the actual weights. So that's that. Okay. So this is one simple linear layer that implements that matrix. So you could just do matrices if you want, but this is how is often done, and it's easier to basically later combine this with other functions. So I can, for example, change the weights. So if I'm not sure if I want to do the change, but if I change this, I'll change the bias and the weights, and you can see that now the weights are, and the biases are changed. Okay, so how do I apply this to, so this is now my linear map, but this is actually an affine map. So if I want to write what this is, so linear applied to X is really W times X plus B. So that's what influence. Okay, so if I apply the linear to this lean object to an input, it applies W to the weight plus B. So if I apply it to this torch tensor, this is a vector which is this is 1 by 2, right? So what it does is it treats the each row as if you remember, so it treats each row as a data point. Okay, and like look at it as like a 2 by 1 vector and then multiplies by the matrix. So what do I get if I do this? I multiply the matrix by this. The first row gets multiplied by this, right?
So it would multiply this by the weights and add the bias?
Yes. So you get the first row 1, 2 times this. Coordinate wise add up plus 1. Right, so you get 1 times 1 plus 2 times minus 2, which is -3, plus 1, -2, right? How about the second one? So 3 minus 8, right? Minus 8 is probably like -4, maybe. -3, okay, good. You're better than me. So -2, -3, -4. And the shape you can see is the same shape as. So you look at the shape, it's going to be 1 by 3. Right? It applied row wise. So the first one was like 1 by 2. It operated on the row and produces 1 by 3. So this is like the kind of batch operation. So if I do it on this tensor, it's going to apply like this. The shape of this is. So let's do this. So you can see the input now has like 4 rows. Okay, so if I apply this lin, what kind of object do I get? It's going to apply the linear map on each row, right? And it produces a 3-dimensional vector. So I did 4 by 3, right? So that's the kind of thing that you would hope to get. Right, you see, this is like the first row of X passed through that linear map gets you the first row here. The second row passed through and gets you the second row here. That it operate like row wise. If you want to do the calculation, you could see that if I call this, for example, W, and I call this B, this is how you can do in Python, you can do this type of operation, right? So you get W and B set equal to those weights. How can I reproduce this? Lean X. If you remember, I have to multiply by the transpose of it on this side and then plus B. So that gives me the same kind of object. Right. So that's the thing that I mentioned. So you do that, like if you want to do the linear operation. Okay, so so these are just some mechanics. Good so far. We have a few, like maybe 2 minutes. I'm gonna move a little bit faster here. So okay, that's what I did here as well. So now this is how you define sort of more interesting objects. The convention is to define a class and then instantiate it to get an object. So this softmax regression would be a model. And so we define a class. This is the name that you can choose. Its convention is to choose like camel case. It's called camel case for class names. And then it derives from NN module. So it's going to be a child of this. So this is going to be the parent of this. So it inherits properties of this, but it also adds like its own properties. So there's some sort of a constructor or like initialization. So you initialize the object here, sort of you set up your parameters and stuff. And then this forward function, all these NN modules have this. So you redefine this. This is how, when you apply your model, it produces the output. Basically, this lin. So this is the forward function of that lin layer. So how it acts on the input. So, well, just bear with me, like maybe 1-2 more minutes. So this is just convention of calling the init function of the parent. So this first initializes whatever the initialization of the parents is doing. And then here we do define a linear layer here. Okay, so that's my softmax regression. It has less theta, a linear layer. So I give the input and output dimensions to my constructor and then initialize this linear layer with that and store it in this linear property. So this solve layer is going to be passed to these functions, and this is going to be the object every time that I apply. So I instantiate an object, and every time I apply these methods on the object itself is passed as the first argument. So I'm going to maybe talk about that later if you haven't seen it, but this is like object-oriented programming. And then in forward, I'm gonna take an input and then apply this linear map that I have on X, and then take the softmax along the second dimension. Okay, so remember the rows we want to keep, the second dimension is like it's going to be mapped to like n by c, and then along the second dimension, which is the columns, basically I take the softmax. That would produce s theta x. Okay, so if I now, for example, instantiate, this is how you instantiate. So you apply, so the name of this would act like the constructor. So when I say softmax regression 2 and 4, it calls this init function with input dimension 2, output dimension 4, and it creates a true model, which is an object of this. And it has a bunch of parameters. It's not defined, so let's define this. So it creates this, and then it has a bunch of parameters, which are basically the parameters of whatever NN modules that you define in this init. So the advantage of this construction is that anything that you define here automatically is registered among the parameters. So true model has a bunch of parameters. When I list them, I get basically the parameters of the linear layer. And then how do I apply it to a data? I can apply model. Let's see if this works. True model. Okay, so if I apply like the true model to X, you can see applies it. True model, when you apply it to X, it just calls this function with the model as its first argument and X as the second argument. And so this would be like model.linear, it's the linear layer of the model, which includes its parameters, applies to X, and then apply softmax, so it produces a result. Okay, because we're out of time, next time we'll come back. But this is on GitHub. I'd encourage you to go through, run it, and like get familiar with the mechanics. Next time we'll go and like go over some more details. Thank you. Bye. Thank you.